Hi everybody, Mr. Stewart here. I thought I would prepare a screencast to help us learn a little bit more about something called trigonometry, which is more or less finding angles and sides in right angle triangles. But before we do that, there are some terms that we need to be familiar with. So, first and foremost, there is a system for labeling sides and right triangles. So let's start with looking at angle A. Angle A is going to be our reference angle. The angle we're looking at, the angle we're using. So across from that, we're going to have what you call the opposite side length. And as you know, across from the right angle, we have our hypotenuse. Last but not least, the remaining side, so the side that helps form this angle, okay, is referred to as the adjacent side length. So my question to you, let's go to the next page, is that if we have angle B now as our reference angle, right, and we want to label those side lengths, where would you place those angles? Or sorry, those side names. So you'll take a moment and complete that, and then we'll have a look at your answers. So, looks like you might have labeled this side, which is across from the reference angle, as the opposite. The hypotenuse you labeled as the longest side, across from the right angle, and the side that remains, the one that helps form the angle you're working with, is known as the adjacent. Okay? So what's important here is the fact that when you change the reference angle, you can kind of see it here. Right? I'm just going to highlight this area. Okay? I'm going to copy that area and I'm going to bring it forward to the next page. And we'll do a contrast. There it is. We'll just pull that into place over here. That's good. So you can kind of see how when the angle changes location, the labels are going to also change in terms of where they are. The only thing that remains static or the same is the location of the hypotenuse. But it's these labels here that are changing due to the location of your reference angles. Okay, just close these notifications. Computer seems to be doing some background checks. So moving on. Okay, so just a quick review here of the fact that similar triangles have what we call ratios of corresponding sides that are equal. Okay, and I want you to take note of that. Have a look at this here. Let's see. Seems as though the board's lost orientation. Let's bring that back by hand. Let's try up here. That seems it. Okay. So for a reference angle of 40 degrees, okay, that's this angle down here. What you can see is that the ratios of opposite to hypotenuse. So I'm just going to highlight those. So this side, opposite, compared to hypotenuse, right, that ratio, also compared, okay, so this one relative to this side length here, those ratios are equal, and that's indicated here. Let's see if I got the right naming. Yes, I do. Okay, 0.64. Take a look at the next one. Okay, we don't have to do them all, but let's look at this one here. Adjacent over hypotenuse. Okay, that would be in the smaller triangle. Here's your adjacent side. That compared to this one, right, that ratio is the same ratio as this full length, or the adjacent in the large triangle, compared to the length of its hypotenuse here. Okay, and that's 0.77 each time. So what we're trying to say is that the ratios, when you compare corresponding sides in similar triangles, those ratios are always the same. Okay? And that you can see through this particular sketch. Just take a look. Watch these ratios here as the angle or the reference angle is changed. Let's see here. It doesn't want to respond, so we'll use the mouse pad for that. So you can see how I'm dragging it up, making the angle larger. Now making the angle smaller, ratios stay the same. And we know that because they're similar triangles. So nothing too new there. So where exactly, where are we going with this? Okay. Well, to be honest with you, if we always had to say this, right, and we always had to use the terms adjacent and hypotenuse and opposite and adjacent, okay, it would take up a bit of our time. So we try to abbreviate that with another term. So the sine of angle A is opposite over hypotenuse. Cosine is the ratio adjacent to hypotenuse. And last but not least, tangent is the ratio opposite to adjacent. Okay? So these new names represent those ratios and all right triangles. So what we'll do is let's take the case of the 40 degrees. Okay, so I'm just going to move this aside. What that means is that we can say, instead of writing this down all of the time, for 40 degrees, what we can say is that the sine, it's abbreviated as such, of 40 degrees is going to be equal to the opposite length BC over AC. And in this case, it happens to be decimal 64. Okay. And interestingly enough, if you use your calculator, I'm just going to grab the calculator here. If I key in 40 as my degree measure of the angle and I hit the sine key, I get a string of decimals. You notice the 0.64, right? So this ratio, sine 40, compares the opposite to the hypotenuse, and in a 40-degree triangle, the ratio will be 0.64. Okay? Same thing applies for the other ratios. So for instance, this one here, the adjacent over the hypotenuse, that's the cosine ratio. So the cosine of all 40-degree right triangles, okay, or triangles that contain a 40-degree angle, is going to be equal to approximately 0.77, because we are comparing, in this case, right, you take the ratio of two sides in this 40-degree triangle, and you end up with that ratio. Okay, so again, on the calculator, just take a look at that. Clear that out. 40 degrees, use the cosine key, 0.766, rounded to the nearest hundredth, decimal 77. Okay, and last but not least, opposite over adjacent, that's the tangent. So the tangent of 40 degrees is going to be equal to 0.84. And those ratios are always the same when you have a right triangle and the reference angle, in this case, is 40 degrees. Okay? But you might be wondering, what if I don't have 40 degrees? What if the angles are all different sizes? Right? Like, what if it was, 34 degrees? What if it was that? Well, using your calculator, you would see that to 4 decimal places, the sine of 34 degrees, okay, which is the ratio of an opposite side length to the longest side, or the hypotenuse, is going to be 0.5592. Okay. What if it's what if it's 74? Okay. What's the ratio of adjacent to the hypotenuse if the reference angle is 74? Well, that's the cosine. The cosine of 74 degrees is approximately, here it is, decimal 2756. Okay, so this particular table used to be what you would find in some older math textbooks. Okay, and it would have all the ratios, for all the angles. Okay, but nowadays, modern technology and scientific calculators can calculate and or has all of these values maintained or stored within their memory. Okay, so let's see if we can't further our understanding with this. I'm just going to check on our time here for video. How are we doing? We're up to 10 minutes. Let's see if we can't bring it to 15. All right. So let's see if we can make sense of some of this stuff. So now it's gotten purely into some new terms and some symbols. We sort of dropped the diagram. So I think we need to bring it back to the triangle, kind of where it all began. So let's grab the right triangle. Just going to sketch one here. And there we go. So let's say we want to represent the cosine of 72 degrees. Okay, so remember, okay, that cosine is the adjacent over the hypotenuse. So what I'm going to do is I'm going to label a reference angle here. I'll just indicate that A is my reference angle. And I mean, roughly, it doesn't look like 72 degrees, but let's say, just for the sake of this example, not drawn to scale, okay, not drawn accurately, that's 72. So across from that, we have our opposite. Our adjacent is right beside it here, forming the angle, and the hypotenuse is over here. Okay, so cosine. Cosine, we're going to be using this side and this side. So let's find the ratio in the table. So that would be over here. So 72 degrees there, cosine 0.3090. Okay, so I'm going to write that down just over here. Cosine of 72 degrees is about 0.3090. So how is that a ratio? Okay. Well, what we could do is take note that all numbers are divisible here by 1, right? And that gives it itself as an answer. So we don't often write it down, but that would represent the other side. Remember, that's the ratio of adjacent to hypotenuse. So if the hypotenuse has a length of 1, the adjacent has a length of about 0.3090. Okay, so that's what those ratios mean in the context of the right triangle. Okay, so I'm going to give you a couple of these to try out and see what you can do to respond to those by a multiple choice. Okay, last but not least, and this will be the questions through your multiple choice. So I'm going to prepare some sketches for these and have you sort of pick out which particular responses you think are appropriate. But I also want you to sketch these into your notebook. Okay, so what do you think the answers are? So go ahead, as you're answering, represent that in your note as well, and also answer it through the Ed Puzzle service. Okay, awesome.